The associated symplectic form is what I call omega standard is minus d lambda, which is equal to dq dq. There's a sign here that for some reason. I'm sorry, but there's a sign. What?
I'm just looking at the representation. So, is it lambda equal to p in that case?
Isn't lambda equal to what?
P. Because p is just the sum of p.
Yeah, you're absolutely, I understand the confusion. Well, let me say it all again. I'm sorry, I just had to repeat. Okay, you have coordinates in the base. That's Q1 through Qn. You have coordinates in the fiber direction. Well, what are those coordinates? Fiber is a form. So it's a linear combination of the dq's. The coefficients are varying, they're functions. So those coefficients are the coordinates of the form. So the coordinates on the product is base coordinate and the fiber coordinate. Fiber coordinate is P1 through Pn, the base coordinate is Q1 through Qn. And where is your problem?
It's just an observation. It's by the fact that what we wrote on the blackboard, they're just the same, right? So lambda is P1 dq1 plus P2 dq2. And then P is just P1 dq1 plus
Okay.
P2 dq2. Which means they're equal. They shouldn't, right?
I'm not yet sure what you're asking. Can you ask it in some other way?
Yeah, right. So you see that you say P is the sum of all the dI's, dqi's, correct?
Okay. So let me even write it this way. dq1 through dqn is a frame of the cotangent bundle.
Correct.
So that means if you have a local section, which this is, it's a linear combination of the frame.
And you write lambda in exactly the same way. So it's P1 dq1 plus other stuff plus Pn dqn. I think
That's right.
the confusion is that why is that not the same thing as P?
Well, because these are functions. The pi are functions. I don't know. The pi are functions, of course, where are the pi's functions?
And then the lambda.
Can we go on how we found the Liouville form again? Maybe this would clarify things. So Liouville form.
Yeah.
So if we studied in the tangent in the bundle direction, what did you mean by that?
The fiber direction. It is 0.
Makes sense.
Huh?
Because it's canonical on that.
It's 0 because it's given by the projection. So,
Is there some sort of sloppy notation?
hmm?
Is there some sloppy notation that's causing?
I'm not sure this is sloppy notation. It's just confusing for a moment.
So lambda is a function. Where does lambda be? Is it?
Lambda, well, you know what lambda is. I defined it. Lambda is a one form on the cotangent bundle space. Right? And as soon as I have coordinates, I can try to write it in coordinates. Right? And therefore, so what are these PIs?
Well, it makes sense to be the same then. I mean, P
What?
is also one form on the tangent boundary space, right?
Because it is trivial on its highway, so it's of the current extents. They are in different space, but it is trivial on the highway, so it can make sense.
So P is one form on the.
So more or less it is just depending on the points.
Pardon me, the P's are not constant.
Now it's Q.
So P is on the manifold, the other is on
Okay. What does this, the question is maybe what this notation means even. I think this is what he was suggesting. Huh? It looks okay to me.
Yeah.
If you apply, look, if you apply this thing to a vector partial of, with respect to Qj, you get Pj. Right? You get Pj, but don't forget it. Pj is depending on where you, which point you are in the fiber. That's maybe the confusing, right? Those are the linear coordinates of the fiber in some sense, Pj. This statement here is this. If I would evaluate this just at a point, this is a basis of the fiber of that point, and these are the linear functions on that point. Those are the coordinates of the point in that basis. I don't think it's confusing. Okay. Why don't you like this?
Why is the notation the same then?
It's the same symbols for the little different spaces.
Yeah, this is, there are two different things, but the same notation. You're right about it. This is writing a one form in a basis. Okay? This is writing a one form in a basis. This is a one form on the manifold. Okay? I mean,
Okay.
Can I say, it's one form on the manifold also written in the basis.
I mean, it's so close to being the same thing, it almost doesn't matter. But I mean, okay?
So PIs are numbers, right?
The PIs are here numbers, and the PIs here are functions. I mean, but it's, okay? And since there are functions, I can take the differential of that form.
Okay, I see.
Okay? So everything here, the Liouville form this is Liouville form. And this is the standard symplectic form. Okay? And physics people will not write wedge. They will forget the wedge and write just dq dp. Okay? Now, so definition. A two form on a manifold a two form, let's call it omega, a manifold is said to be symplectic if it's closed, and non-degenerate. Everybody here understands closed. We should understand what it means non-degenerate. Okay? So, omega maps tangent bundle across the tangent bundle to a function, to real numbers, is non-degenerate whenever omega v point is 0 implies that v, see, I've been a little sloppy here, but you understand that? So you have experience with bilinear forms. You put a vector in the first argument, you get a linear function. If this is 0 as a linear function, the only way that can happen is if v is 0. Okay? I like to write Tm perp with respect to omega is 0. The set of vectors which is orthogonal to everything is the trivial vector. Okay? Now this does not mean that there are no vectors of length 0. You know this, with the things on the boundary of the light cone, of course, are norm 0. Right? But they're not orthogonal to everything. So that's what this is. So a fact that you can easily check is omega standard is symplectic. On the cotangent one. Okay? And you can check it just in coordinates here because it's just this thing. Okay? Now, the last remark and then we can quit for today. I'm sorry, you're probably very tired. This is a very beautiful remark. It's called Hamiltonian mechanics. Hamilton's idea. You start with a Hamiltonian. He didn't call it a Hamiltonian, but you start with a Hamiltonian, which is any function, and you take d of this. And you say that's a one form. That's a one form, right? But if you have the standard symplectic structure, that's a one form, I can contract, this must be equal to the contraction. Here's an incredible idea. With some vector field. I don't know your notation from, do you use that as contraction? Let me just write it out. It's this. You just put it in the first argument and you get a one form. And since this thing is non-degenerate, that's a really well-defined guy, right? Okay, so this is a mapping from functions to one form to vector fields. Okay? From one form's functions to vector fields. Suppose you have coordinates, like we have here for the whole lecture, Q and P. We will see next time when I start introducing you to the symplectic methods here, what this thing is. This thing is, well, now I'm going to make sure I get it right. What should I do first? I'm sorry. Did I get it right? I hope I get this vector field over here. Check with me on that. The vector field over here is right? So the integral curve of this vector field would be Q point equals plus or minus dp. Minus dp and P point equals dq. Okay. So you see that in fact our vector field that we have here is a Hamiltonian field for some Hamiltonian function on, well, we know what it is. So this is the Hamiltonian mechanics picture. Okay, I know you're very tired of this tough day. Okay, so I don't think I need to repeat it, but I'm going to just because we have a little bit of time. We start with, let's not even write, let's just think together. We start with the notion of a geodesic defined by a connection. Very intuitive, but the most intuitive thing is a geodesic defined by distance, or length. We realize that in order to find the critical points of the length function, it's the same thing if you use arc length or curve length as parameter to find the critical points of the energy function, of the action. To find critical points of the action, you do calculus. You take the derivative of the action, right? With all perturbations of all curves nearby with the right endpoints. Right? You do that and you find the Lagrange equations. That is in fact a completely general thing. You have the integral of some Lagrangian and so on, you find the Lagrangian equations. Okay. That is something on the tangent bundle. The cotangent bundle, as it turns out, is much better than the tangent bundle because it has, God gave it structure. So we're hoping to use the structure from God somehow with these Hamiltonian equations. So we take the Lagrangian, transform it by the Legendre transformation to the Hamilton equations, and we find that we have these wonderful Hamiltonian equations. Then we see that on the cotangent bundle, this guy, lambda, is, although it's a little bit confusing, that's the guy lambda, and d of this lambda is the right symplectic form to discuss. Once you have a symplectic form, everything's canonical now. Once you have a symplectic form and a function, you take d of the function, and that's a one form, and that's equal to a contraction of a unique field of this two form. This is a mapping from functions to fields. Every physicist knows this. This is a mapping from functions to fields. Some physicists will do this and say that's an operator as a vector field, and they will write this Poisson bracket, as you know. This is a mapping from functions to vector fields, and this mapping looks like this. Now what do you know? The exact thing that we got by Lagrange, like the Legendre transformation, is exactly a Hamiltonian system in this way. Okay? And therefore we have a much better place to look at this whole thing, namely the Hamiltonian mechanics of the quantum. Okay? I will spend all next week talking about symplectic geometry and how this plays a role in everything here that we've seen. Okay? It's also a lot of fun, symplectic geometry. Okay, thanks for your patience today.